Okay. Hello, everyone. Welcome back to the undergraduate seminar. Today, we've got Julie Midroni, who's going to tell us about artificial neural networks, going to introduce us to the fundamentals of this super important field. So Julie, take it away.
All right. So hopefully everyone can hear me. If I ever cut out at any point, just stick it in the chat and I'll repeat whatever it is I've been saying. So my name is Julie. I am a fourth-year undergrad at the University of Toronto studying physics. And it just so happens that the research I'm doing under my professor has a lot to do with artificial neural networks. So I thought this would be a good time to kind of introduce something that is becoming more and more relevant to research to a lot of people. So I'm going to get started with this. We're just going to cover the fundamentals today. And if anything is super unclear, feel free to also stick that in the chat and I'll do my best to clarify it. So please let me proceed. Yeah. Okay, so in order to explain what artificial neural networks are, we have to motivate their existence. So artificial neural networks on a very, very general level are designed to solve a specific problem, which is getting a function, a mathematical function, to spit out the correct vector if we feed it the correct numerical input. Now, that's incredibly general. We haven't yet defined what correct or what the right vector means. And that's something we'll talk about later. But the general idea is that we want a system that if we give it an input, it will spit out an input that we want. And that seems incredibly straightforward. I mean, even y equals mx plus b does that for us, right? If we know what line we want, we stick in a number, we get a number out. But the way that artificial neural networks are designed, they actually are able to deal with far more complex problems than that. So let's take a kind of look at what the things that artificial neural networks deal with might be. So this is a decently straightforward example, but what if I only have a few points and I want to create a function that can describe the behavior of these points? Now, obviously, this is something that falls under the type of problem we're talking about. We want to be able to input something and get out the image of that as according to the trend from the original points that we had. Now, obviously, this is very straightforward. A regression will do this for you most of the time, but this is something that an artificial neural network could technically do for you. Now, more interestingly, what if I want to classify pictures? Now, this is the classic artificial neural network situation. What if I want to be able to say, this is a cat, this is a dog, and this here is a really low quality picture of Abraham Lincoln? Well, pictures are actually just tensors, typically 4 by whatever, which have numbers that represent the intensity of the colors of pixels, right? So pictures are just tensors. And I want to create a function that takes in a tensor of a certain size and outputs a 1 if it's a cat and a 0 if it's a dog. That's image classification. And that's something that falls under this umbrella of problems, right? We want to put in a numerical input, we want to put in an input tensor and get out a number that we can then interpret to represent either cat or dog. Even more interestingly, how do you think we make chatbots? Like, I don't know if any of you have ever played with Cleverbot as a child, right? We convert words to numbers using a dictionary. So we say, okay, the word the is a 1, the word and is a 2, and so on and so forth. And then we train this function that we're talking about to recognize input sentences and then spit out an output vector that makes sense in context, right? That is able to interpret the numbers and say, okay, well, what string of numbers would make sense to return? And then we can take that string of numbers and reinterpret it into a sentence. So there's some crazy complicated applications for this very seemingly simple problem, and we definitely don't have time to go into all of it today. We're not going to go into image classification in detail. We're not going to go into chatbots and natural language processing. We're just going to talk about the very basics, the building blocks of the most simple artificial neural networks. And if you're interested, there's plenty of literature you can take a look at in order to learn more. So in order to talk about an artificial neural network, we have to start with artificial neurons, because these are the building blocks of artificial neural networks. So let's talk about what one of these artificial neurons is made out of. It has 4 key components. So the first one is an input, and the input is going to be each component of a tensor. So if our tensor is just, a one-dimensional vector, it's for example, I have an input of 1, 2, 3, right? Very simple, very straightforward. Then I'm going to input each of these components into my artificial neuron. So that's going to be my input of 1, my input of 2, and my input of 3. The next component of an artificial neural network is the weights. Now, the weights are really important. The weights are what allow us to make the artificial neural network flexible, and we'll talk about what I mean by that in a few slides. But basically, how the weights work is they become a multiplicative factor. You're going to take this, you're going to multiply it by the weight, and you're going to pass it on to the next part of the network. So here I have, say I have a weight of 1, here I have a weight of 2, and here I have a weight of 5. Well, 1 times 1 is 1, 2 times 2 is 4, and 3 times 5 is 15. So I'm going to multiply all those together. And then in the next step of the network, I'm going to add all of those values up. So I'm going to add up 1, 4, and 15, and I'm going to get 20, right? So this value here ends up being 20. And the last and one of the most critical parts of the artificial neuron is we then apply some sort of activation function, right? The activation function is typically some nonlinear transformation of the data. For example, some sigmoidal function we can apply or a thresholding function. And after we apply it to the sum, that gets spit out as the output, right? So we multiply, we sum, we apply a function, and then that becomes the output of the artificial neuron. It's pretty straightforward. Okay, so this here is an artificial neural network. Now what we do to make these is we chain multiple artificial neurons together. So it's a series of linear transformations, which is the adding, and then the nonlinear transformations, which are the activation functions. And they allow for an input, which is going to be over here, over multiple steps to be converted into a correct output. So in this case, we have 2 steps. We pass to this neuron, and then we pass to this neuron. And I'm going to walk through exactly what that means on the next slide. So what we call this is forward propagation. When we take the input, we stick it into the network, and then we get the output. So we're going to follow forward propagation just to this one neuron because I don't want to have to do it for all of them. Suppose I have some input, and my input is, we're going to call it x1, x2, and x3. Sorry, my handwriting is really bad. Okay, so we're going to take each of these inputs, and then suppose we have this connection here, and this connection is weighted, right? We have our weights. We have our weights W1, W2, and W3, right? We have this neuron here, this artificial neuron, which has 3 inputs, 3 weights, and it's going to spit out an output. Okay, so what are we going to do? We're going to take each of these, we're going to multiply them by the weights, and we're going to sum them up, right? So we're going to get some sum, which is like I equals 1 all the way to n of xi wi, right? Okay, that's going to go in here, and we're going to call that, let's say, a, right? So that's our sum, and then we apply some activation function. So what we get in here, we'll call the activation function f, is we get f of a. Wow, my handwriting is horrible, right? And then f of a is going to get spit out as an output, and it's going to travel down to all the subsequent connections that are connected to this neuron. So this f of a is going to go here, and it's going to go here. And in that way, right, we have the summing, and then we apply a function, and then we pass that on to all of the neurons that are connected downstream of that one neuron. And that's just one neuron. We're going to do it again and again for every single neuron in this hidden layer, and then we're going to do it for all the output neurons. And then each of the output neurons will give us some number that we will interpret in context. So that is forward propagation. I hope that was clear. If there are any serious conceptual issues in how I explained it, feel free to let me know. Okay. But in order to talk about why we need this complex web of nodes, because going back, like this is a lot. And this is an incredibly simple neural network, right? A lot of neural networks can be thousands of neurons wide, thousands of layers deep. They can get very, very complicated very, very quickly. So the question is honestly, like, why do we even want this? Why can't we just do something far simpler that's going to accomplish the same thing? Well, in order to understand why we need all of these activation functions and neurons connected, we need to understand what linear separability is. So for people who haven't been introduced to this definition, we call 2 sets of points in some n-dimensional vector space, A and B, linearly separable if there exists some n+1 points, such that for any point A in the first set and B in the second set, these 2 inequalities hold. And I'm going to interpret this, so don't worry, because I know reading definitions off a slide is like the worst thing ever. Been there, done that. So what does this mean? Well, the equation for a hyperplane in some n-dimensional space is this is the equation for a hyperplane in some n-dimensional space where we have, a sum over n points with coordinates, and then we have some other constant which is going to help define the location of the hyperplane. Now, if we look at this part here, or we rearrange this, right, and we get the sum of wi xi equals omega naught, and we look at this inequality here, and we look at this inequality here, what we see is that all this definition is saying, which n the integers, yeah, it's the same n as in Rn. Yeah, thank you, Albert. All that this definition is saying is that all of the points in A fall above the hyperplane, and all of the points in B fall below the hyperplane, defined by the weights and by omega naught. Okay, so that's all that linearly separable means. It means that, oh no, so the ends are from 0 to, sorry, the index is from 0 to n. So they're n plus 1 points, and I've indexed them 0 to n. I'm sorry if that's unclear. Right, so the sum is from I equals 1 all the way to n. And then we have the index 0 over here, which is our constant that helps define the location of the hyperplane. Okay, so linearly separable, all that means is that we can define some hyperplane that separates these two sets neatly, right? So all of the things in one set are going to be greater. When we evaluate the left-hand side, they're going to be greater than that omega w naught. And when we evaluate all the points in another set, it's going to be less than that w naught. Okay. Why is this important? Why do we actually care about this happening? Okay, so I'm going to clear this, and we're going to go over why this is relevant to neural nets. So what an individual node, what an individual artificial neuron node, artificial neurons are the same thing, without an activation function does, is it evaluates the left-hand side of these inequalities. Hopefully we can all agree on that, right? Because if you have your node, if there's no activation function, all it's doing is spitting out the sum of the inputs and the weights, right? That's all it's doing. If we're not applying a function here, we're just multiplying and we're summing, right? So all we're doing is we're evaluating this left-hand side where the wi's are the weights for that particular node. Okay. Now, if the data we are working with is linearly separable, then there will be some constant omega naught such that when I evaluate this sum and this product, all of the points from the first data set, for example, the cat data set, will be greater than w naught, and all of the points in the dog data set will be less than w naught. Now, I may not know what this constant is, but the whole point is that some constant will exist by definition if these two data sets are linearly separable. Okay, so why is that important? Why do we want the data to be separable under this transformation? So let's take a look at why. Okay, what we need to remember is that oftentimes what these networks do is they classify things. And when we classify things, we do it in neural networks by thresholding. So we want our network to output different numbers based on the input in a way such that we can say, if the number is in this range, it is a cat. If the number is in this range, it is a dog, and so on and so forth. Or alternatively, if the first index of the output vector is the greatest, it's a cat. If the second index of the output vector is the greatest, it's a dog, and so on and so forth. Okay, now, saying that once weighted and summed, all the data in the cat group, for example, is greater than a certain value, and all the data in the dog group is less than a certain value, right? Being able to do that thresholding, which is what we want our network to do, it means that the numerical representations of the cat and the dog data are at that point linearly separable, right? That's the exact concept and definition that we just walked through. And if it's unclear to anyone, I'll gladly go through it again. But the idea is that if we want to be able to threshold without these activation functions, the data has to be linearly separable, because once we apply the weights and we apply the sum, it's either going to be greater or less than a certain value, and that value only exists if it's linearly separable, right? There's only a value where we can say if it's greater than this, it's a cat, and if it's lower than this, it's a dog, if it is linearly separable. Okay, so if the data is linearly separable, that's fantastic. We can just take one or two very, very few nodes without activation functions and evaluate everything. It's not even going to be remotely difficult, right? We'll have everything figured out in a jiffy. But the problem is, it's very, very unlikely that our data is actually going to be linearly separable right out the gate. Now, why is this? It's because images and other more complicated tensors, they're very complex, right? If we have data of cats and cats, the pictures of cats can change very, very wildly depending on even the species of cat or like the angle of the picture of the cat that you take, right? it's very unlikely that the tensors that represent the cats and the tensors that represent the dogs are going to be able to be neatly sorted, or the vector that represents the cat if you want to do a different representation, and the vector that represents the dog. So what we need to do in these cases is we need to convert our data into something that is linearly separable. Okay. Now, for example, we have this picture here, right? This data here clearly isn't linearly separable. Now, this is a set of data in 2D. In 2 dimensions, a hyperplane is just a line. But no matter how many lines I draw, there is no conceivable way for me to separate red and blue with just a simple line, right? So this data, even if I put it through a bunch of nodes, if they don't have activation functions, they're completely linear. It's not going to be able to separate the data, and then I won't be able to say, okay, if the network outputs a number in this range, it's red, and if it outputs a number in this range, it is blue. So how do we deal with it? Well, multiple nodes, layers, and nonlinear activations transform our data into something that is linearly separable. What do I mean by that? By mixing inputs and applying nonlinear transformations, we are able to gradually, across layers, take our data and warp it such that the output is linearly separable, so that different classes can then be separated. So this is a diagram that I took from a paper, which you can find in the references, and I will be giving the slides so that people can take a look at this if they're interested. But basically what the authors did here is they just took a very simple neural network, only 2 hidden layers. You have your input, you have your hidden layer 1, you have your hidden layer 2, and it's only 2 neurons per hidden layer. And they took this input that is very clearly not linearly separable, and only in 2 layers using, I think it was just a simple sigmoidal activation function, though I could be wrong, the output becomes linearly separable, or almost linearly separable, right? If I draw a line there, we do a pretty good darn job of, partitioning it. So hopefully now you can start to see the power of these neural networks, right? Even a simple network like this can take something that is clearly not linearly separable, make it linearly separable, and then we can interpret the output as we want to. Now imagine if it wasn't something this straightforward, like a circle within another circle. Imagine if it was something very complicated, like a really, really, really high dimensional tensor with a lot of different features. But we can make the neural network really, really, really big. And ideally then, it will be able to exercise these exact same principles to take this data and turn it into something that we can actually interpret the output of. So, part 1 summary. Artificial neural networks do what we want them to do. And if we add a lot of neurons, well, we can get them to do a lot of things. And I'll talk a bit more about that at the end. Right, so in more formal terms, given an input, so long as the weights are correct, and we'll get back to that, an artificial neural network will return an output with a numerical value that either represents the class of the input or is the image of the input as transformed by some unknown function that we are trying to approximate. And the important part here is that this is regardless of whether or not the input can be linearly separated. Okay, so you may notice that on the previous slide, I said, given the correct weights, because obviously the output of an ANN is going to depend very significantly on the weights that we choose to use, right? Because we're multiplying our inputs by them. The weights can be huge, they can be tiny, they can be positive, they can be negative. So we need to pick the right weights such that we can get the output that we want, such that the data is actually separated or the data is otherwise transformed in a way that we can interpret and in a way that tells us what we want. So how do we determine the weights? Well, this is machine learning at the end of the day, so we do this by training. When you decide to make an artificial neural network, and you should because it's decently straightforward and pretty fun, you need a data set on which to train your artificial neural network. So this here, I have an image of some pictures from the MNIST data set, which is just a set of handwritten numbers, and it's used to train neural nets that can say, okay, this is a 1, this is a 2, this is a 3. And again, may seem very obvious to us, but it's not obvious to computers, right? They have to learn to deal with things like this 1 being the same thing as this 1, or this 5 being a 5 when it's clearly just a squiggle, right? So teaching computers to do things like this is not at all straightforward. But okay, let's talk about it. So, like I said, you need your training data set. You need a data set upon which to train your neural network. Now, what you're going to do is you're going to take your data set and you're going to split it into a training set and a test set. Now, if any of you have done machine learning before, you know the importance of train test. For those of you who haven't, it's like a whole section of data science. I'm not going to go into it too much. But the general concept is that you need to split your data set into a training set and a testing set because the training set is what you use to update your neural network, and the test set is what you then use to confirm that it works after you've updated. If you train on the test set, that's like showing a student the answers to the actual exam when all they should be using are the practice tests, right? If you then evaluate them on the actual exam and use that for their grade, that's cheating because they already knew the answers. It's the exact same concept with train and test. So we have our test set, suppose. And now we're going to do backpropagation. So backpropagation is how we train artificial neural networks. It's a weight update algorithm. So we're going to go through all the steps that I've listed on this page in detail. So don't worry about them right now. But this is basically backpropagation is how we're going to update our weights in our neural network. Okay, so the step one of backpropagation is the forward pass. We're just going to forward propagate the data through the network. This is exactly what we talked about before. We're going to take our images or our vectors or whatever it is we want. We're going to stick them in the neural net and we're going to get a result. And this result may or may not be correct. Now, what do I mean by correct? Well, when we generate our data set, every input in our data set has to be matched to an output. And the output is the theoretical output. It's the output that we want to get. So if my input is a picture of a cat, my output might be the number 1, right? And what that means is that if I put in a picture of a cat, this picture of the cat, my neural network should output the number 1. This is what the neural network uses to check its actual results against what it should be getting, right? Because the neural network can't be like, oh, I know that's a cat, but I said dog, right? Like they're not humans, obviously. It's just a piece of code. So what we're going to do next is we're going to calculate the error between what we should be getting and what the neural network actually gives out. So I'm going to use a few pieces of terminology just for the rest of this presentation. We're going to call our piece of training data X, right? So that's our input. We're going to call Y sub T, or theoretical Y. It's going to be the expected or the correct output, the output that we want. And Y sub E is the actual output of the network. It's the output that the artificial neural network gives us. So what we're going to do in order to calculate the error is we are going to define some differentiable error function, E of Y sub T and Y sub E, that represents the error between the expected and actual outputs. And there are like a million different error functions you can use. A whole part of designing a neural network is figuring out which error function is good for you. We won't go into that too much, but the point is we need some differentiable error function, and I'll talk more about why it needs to be differentiable and what that means later on. But anyway, so we call the error of this output the loss, and the goal of a neural network is to minimize the loss, right? We want to say, okay, no matter what input I put in, I want this loss to be as small as possible. I want it to return the wrong value the smallest number of times, right? So what we want to do is we basically want to minimize this function E right here. All right, so what we're going to do is we're going to update the weights to minimize the loss. We can't control the input that the neural network gets, right? I have to be able to put in any picture of a cat or a dog that I want. We can't control the activation functions once we've decided them. Technically you can add adaptable parameters to activation functions, but we won't get into that. The point is the main thing that we can control in a neural network is the weights themselves, right? Those things that we multiply each input by every time it gets passed to the next neuron, there's like a million of those in a large neural network, and we want to fine tune those to minimize the loss function. And to do that, we're going to use the backpropagation algorithm, which employs everyone's favorite calculus rule, the chain rule. Okay, so first of all, for those of you who have forgotten your second year calculus, recall that the gradient of a function is a vector of the partial derivatives of the function with respect to each component. And all of these functions that we're talking about, we can define the gradient because they're all mapping to just R, right? We're not getting anything that's mapping to R2 or R3 or anything. They're all mapping to R. Our loss function spits out a number. Each node spits out a number. Our activation function spit out a number, right? But they can have multiple inputs, right? So our gradient, for example, if our function has 2 inputs, our gradient of F would just be, the partial of F with respect to X, and then the partial of F with respect to Y. Okay, great. So what we have to remember is that if the gradient is positive in a particular direction, then the function is increasing in that direction for that component, right? So if the partial of F with respect to X is, oh dear, I think my pen just died. Okay, I'll use my mouse. If partial of F with respect to X is increasing, at a certain point, then that means that as x increases, f is also increasing, right? And that's going to be a very important principle for us later on. So remember, the goal of this is that we want to minimize e, our loss function. We want to get e to be as small as possible. And we're going to do that by getting the gradient of e to be 0, or the gradient of e with respect to the weights to be 0. Now, I know this doesn't guarantee that something is minimized at all, or that it is globally minimized. It could be locally minimized. It could actually be maximized. This is a well-known problem of the backpropagation algorithm. We'll talk about it more later. But for now, just bear with me and assume that this works the way it's supposed to, and that it will find you your global minima. And I mean, it will if the loss landscape is like reasonably nice. Okay, so remember, e was defined as a function of the output, and it is thus a function of the input and the weights, which are going to be w1 through wk. Now, we don't know how many weights there are. We're just going to say there's k of them. K can be any positive integer because we don't know how big this neural network is. Okay. As I said, I'm going to say it again because it's important. If the gradient of e with respect to a particular weight, w sub I, is positive, that means that e is increasing as we increase the value of that weight. So what we want to do to counteract that is we want to decrease the value of that weight in order to try and move e closer, closer, closer to its minimum. Okay. So through this, we define a simple weight update rule. Now, there are many variations on this weight update rule. There's a lot of things that can make it slightly more efficient. We'll just go with the basic one. We find the new weight by taking the old value of the weight and subtracting from it L multiplied by the partial derivative of the error function with respect to that weight. Again, remember, so if the partial derivative of the error function is positive, that means that as we increase W, E increases, so we want to decrease W, right? That's why we have this negative here. Whereas if this ends up being negative, we want to increase W, negative, negative gives us a positive, so we end up adding a value to W. Now, what L is it's the learning rate of the network. And what the learning rate of the network is it's just a parameter, typically predefined, but you can have it change throughout training if you want, that controls how much influence the gradient has on each individual weight update. It can be very large, it could be very small, and later on we'll talk about the pitfalls of it being too large or too small. Okay, but how do we actually find this partial derivative, right? Like this thing here, that's not something that we automatically know. So how are we going to go about finding it? This is where the chain rule comes in. Okay, so E, right, our error function, it is a function of the output Y, right, the experimental output YE. YE, in turn, is a function of the layer's input Z. And Z is a function of the previous layer's output and weights, right? So if I have my error function here, so I'm drawing with my mouse because my stylus died. So if I have my error function here, right, that is a function of the output Y, right? And Y in turn is an output as a function of the output of the, or the, Y is a function of the summed inputs of the neuron Z. And Z is in turn a function of the previous layer's input and weights, right? So it's going to be a function of whatever was shot out from here and a bunch of weights, right? Like WI. Okay, why is that important? Well, what it means is that since E is a function of YE, and if YE has multiple components, then we can define the partial for each of those components, right? Since E is a function of YE, the partial derivative of E with respect to each of YE's components exists. And since YE is a function of the layer's input Z, the partial derivative of YE with respect to Z exists. And since Z is a function of the previous layer's input and weights, the partial derivative of Z with respect to each of those weights also exists, right? All of these things exist. They are defined. They are properties of this network. And all we need to do in order to get the partial derivative of E with respect to a particular weight is use the chain rule. Just multiply them together and we get exactly what we want. And the lovely thing about it is that since we know all of these functions, we chose these functions when we designed our neural network. Since we know what the value of Z is because it's just one of the outputs of our network, so it's a value that is recorded when we do a forward pass. Since we know all of these things, we can actually just evaluate this and get the numerical value for the partial of E with respect to any weight WI. And if you want to go further back, say that, we have a bunch of layers in this neural network. We want to go all the way back here, or we have 1,000 layers. We really want to go way far back. All we need to do is keep using the chain rule to go over here, or go over here, or go over here, or wherever it is we want to go. So that's backpropagation. I hope that made sense to everyone. In summary, we do our forward pass, we calculate the loss, and then we backpropagate and update our weights using our weight update rule. And then what we're going to do is we're just going to rinse and repeat. We're going to do it again and again and again, thousands or millions of times until we've reached a satisfactorily low level of loss, or until we've run it so many times we just want to stop and use it anyway. That's fine too. So that's how you train a neural net. Those are the fundamentals. There are a few other tweaks you can make, right? So there you can do something called batching, which is when you train things in batches instead of doing the backpropagation after each individual thing you put in. There's some advantages to that. There's a whole bunch of fine tuning basically you can do with a neural network. And one of the things I think that people don't necessarily appreciate right off the bat is, okay, neural networks, incredibly powerful tools, but they're not like omnipotent computing gods. If you want your neural network to work well, you have to spend time kind of picking the lock on your own particular problem and testing out a whole bunch of different variations, maybe reading some literature on what works well for your problem, testing out different batch sizes with like smaller test sets. There's a lot of fine tuning to be done if you create a neural network for a problem that like a lot of people haven't already done. Okay, so there's some other issues, and there's one here that I forgot to write down that I'll also talk about. So the first ones are the concepts of local minima and the learning rate, which I alluded to before. But basically, as you might imagine, if our strategy for minimizing E is just to make the gradient with respect to the weights 0, I could end up in a local minimum, I could end up in a maximum. Now, the chances that I'll end up at a maximum are pretty low, because if I'm even slightly off, then the next weight update will just shoot me over to the other side and then I'll fall down the maximum. But in terms of local minima, that is a genuine issue that a lot of algorithms run into, right? If the loss function has more than one minimum, then if you're just going for the gradient being 0, you could end up in one of those minima, and we don't want that. So the way that we deal with that, right, is we use a larger learning rate. A larger learning rate means, if this is a local minimum and I'm down here, let's make this a hump that goes down to like the global minimum. If this is a local minimum and I'm like over here, right? If I have a large learning rate, there's a chance I could end up all the way over here. And then I'll just slide down to the global minimum, and that's great. The pitfall of this, though, is that if it's too big, I could also end up shooting myself right out of the global minimum, which obviously is not something that we want. On the flip side, though, you don't want to have too small of a learning rate, because then, like I said, you'll end up in a local minimum, potentially. That's not something that we want either, especially if we need this neural network to have really, really high accuracy. Okay. The other problem that I want to talk about real quick is something called the vanishing gradient problem. So and this is actually a really significant problem for large neural networks. So we talked about backpropagation over here. And already you can see that just to get the value of the gradient with respect to one of these weights, we have to multiply 3 partials together. Now, what if I want to go 4 layers back, or 5, or 6, or 7? If the gradients are all less than 1, the gradients are going to become very, very, very small, very, very, very quickly, right? The gradient of E with respect to Wi, if Wi is all the way back here, like 10 or 20 or 100 or 1,000 layers back, it's going to be pretty tiny. And if we look at our weight update rule, what that means is that the weight is barely going to be updated at all. And that's what we call the vanishing gradient problem. It can make adjusting weights far back in a neural network very, very, very difficult, which is why a lot of more fancy newfangled neural networks have been created to kind of try and avoid this problem that we have in a standard classic feed-forward network, like the one that I've just told you about. Okay, so let's summarize. Intuitively, what are these artificial neural networks actually doing? We've walked through the math, but what does that mean to a human brain, right? By adjusting the weights, artificial neural networks pick out which inputs are important in certain circumstances. What do I mean by that? Well, the weights are chosen to notice patterns in inputs. and produce different outputs with the same weights depending on the presence or absence of certain features. What does that mean? Well, suppose I have two weights, and one of those weights is a -1, and one of those weights is a 10, okay? And I'm gonna pass them to this node. Well, if my input is, let's say 1, 0, very simple, then what this node is gonna get is it's gonna get -1, right? On the flip side, if my node is 0, or if my input is 0, 1, it's gonna get a 10 instead. Now, why do we care about that? Well, if I'm trying to classify, say, cats and dogs, and most cat pictures in the top right of the picture, they have a lot of dark colors. So the numbers in that top right of that tensor, they're all going to be really, really, really low. Whereas for dogs, that's not the case. Well, even though the neural network has the same weights in all situations, it's going to respond differently because there's a lot of low numbers for cats and a bunch of high numbers for dogs. So we're going to get different values propagating throughout the network. The amazing thing about neural networks is that it does this, and through training, through minimizing the loss, if you have a well-defined loss function and you use the right optimization algorithms, it's going to be able to pick up things that let you distinguish between cats and dogs that you wouldn't even notice as a person. I mean, obviously, you don't need to notice them because you look at a cat, you say that's a cat. You look at a dog, you say that's a dog. But it's able to pick up on what we call features, or small elements of an image or an input that we don't even know that are important, and it'll automatically begin to prioritize those aspects of the input using certain patterns of weights. So hopefully you can see this is far, far more powerful than a simple regression. And importantly, it's also robust to small changes in the input, right? A neural network that differentiates between cats and dogs will be able to tell ideally that different species of cats are still cats, because it will identify features that are unique enough to cats to identify cats, but not so unique that they only identify specific types of cats. Okay, so let's do a quick demo right here. Right, so this is, hopefully you can all see this. Oh, you can see my browser, right? Just stick it in the chat if you can. Okay, perfect. So what this is it's just a neural network visualization from a Python package called TensorFlow. TensorFlow is not my neural network program of choice, but it certainly is a package that you can use if you want. And basically what we're going to do is we're just going to construct a neural network for fun. We're going to see how it works. Okay, so we're going to pick a data set. Which data set do you want to use? We could use the spiral data set. We can use the circles. We can use the checkerboards. This one's boring, so I don't want to use it. Someone tell me in the chat which one you want to use. Spiral? Okay, we got some votes for spirals. Okay, so we'll do spirals. And this one does look pretty tricky, okay? So let's take a look at what we want to do. So we have a learning rate that's kind of moderate. We'll keep it like that for now. We'll use, okay, a tanh activation function, sure, whatever you want. What we're going to do now is we're going to say, okay, we need to decide, first of all, how many hidden layers. Now, the general rule for neural networks is more hidden layers is better. After a certain point, it becomes redundant and computationally inefficient. But let's add another one just for fun. And let's add more neurons to it because we can. All right, so now the other thing we need to pick is we need to pick how we want to import the data. Now, obviously, sometimes we can just stick in the data as it is. We can say, okay, I'm going to give you the x coordinates and the y coordinates, and you do your work. But what you're about to see here is that actually, if you transform the data before you stick it in, it can be trained. The neural network can actually work with it a lot more efficiently. It's like adding in nonlinearity right off the bat. So let's start by only doing x1 and x2, right? We're only importing the x and y coordinates exactly as they are. We're going to train it. We're going to do a bunch of rounds of training. And as you can see here, right, our loss is still pretty high. It's a 0.5. We want it to be way smaller than that. And in addition, even though the blue and the orange are in spirals, the background, which shows which regions of this space map to blue and which regions of the space map to orange, as per the neural network, it's not actually giving us all we want. All of this blue stuff up here is being mapped to orange, and all of this orange stuff up down here is being mapped to blue. So let's try adding in a bunch of other stuff. Let's say we want to also add in as an input the product of these two inputs. Okay, well, that didn't do too much to help us. We're getting a bit better, actually. Oh, wow, look at that. The loss is now dropping significantly, and we're getting some very, very, very interesting looking space. So let's pause it right here for a moment. So already, what you can see, even if our loss function isn't too good yet, is that we're able to take the input space and transform it into something very, very, very not linearly separable, on something that is beginning to look, curved, and that is able to differentiate between different areas of the space, even if it's not the spiral that we want it to be. Okay, let's try taking the sign of the first coordinate as well. Now let's see what happens. Oh, we're going down. Oh, look at that. That's bizarre. And it looks like we're getting stuck somewhere around here. But again, you can kind of see that areas of blue are starting to be cut out around the areas of orange, right? We don't need this space, this mapping space, to be perfectly in a spiral. We just need it to be shaped, even if it's incredibly ugly, such that all of the orange goes to orange and all the blue goes to blue. Let's try sign transforming the second coordinate as well. Okay, we're speeding down. Oh, wow. Okay. And look, we could keep going on forever and ever and ever with this. And obviously, we haven't even tried to add more layers. We haven't tried to change the learning rate or the activation function. And already, you're kind of starting to see these you're starting to see these spiral shapes beginning to emerge, right? And this is very straightforward, just a very simple feed-forward network. Like I said, we haven't changed any of the other parameters. So it's pretty incredible how even just doing something like a simple exercise like this can kind of show you how much a neural network can transform the output space into something that can fit almost anything that you want it to fit. So let's go back to the presentation. And let's talk really quickly about a few more advanced artificial neural networks. I'm not going to go into them in too much detail, but I'll give you kind of an idea of what they may be. So the first ones are recurrent artificial neural networks, and these allow for time-dependent data. So what a recurrent ANN does is it takes the output and it feeds it in as another input, right? So if I have, a vector of like 1, 2, 3, 4, 5, but each of those numbers is actually the subsequent time step for a data set, for example, then I can feed those into the recurrent network. And at each time step, it'll take a new input as well as the output of the previous time step. So what it basically does is it takes the previous conditions into account in order to decide what the next output should be. Like I said, really good for time course modeling, really good for chatbots where you want, obviously the previous word in a sentence impacts what you want the next word to be. So it's able to take those kinds of things into account and you don't get a word salad. We also have convolutional neural networks. They're really good for image classification. This is typically what you would use for like a cat dog kind of problem. Basically what they do is they take an image, they will identify certain sections of it, compress them down, extract the main features and kind of make everything smaller and smaller and then pass it through a feed forward network. The value of these is just that if you have a really big image, you can still deal with it. And they're also able to better recognize patterns in images like, oh, well, this section of the image is a cat ear, because, you're kind of taking different sections of the image and taking a look at the features in each of those individually. So I'm all done. I'm happy to take questions, or if anyone wants to take a look at the demo again, if anyone has any questions about coding artificial neural networks, I'm happy to talk about any of that.
Awesome. Thank you so much. That was like a fantastic talk. And I think I really learned something about neural networks. Before we get into questions, I just want to share the feedback form. So we're going to give Julie a 3-minute break before we get into question period. So in those 3 minutes, please fill out this Google form. Let us know what you thought. I thought that was an amazing talk. So we'll meet back at 2:52 Toronto time.